everyone, welcome to this video by DataSense. So far we have covered the major time complexities such as constant time complexity, linear time complexity, polynomial time complexity and exponential one. Now this video is about one of the most efficient time complexity which you will find and something which you will be using lot of time when involving arrays, lists, those kind of data structures. This is called logarithmic time complexity. Now, this is specific to some of the tasks that you will be getting in future. So, because I have not explained lot of algorithms to you guys right now, so it might be initially difficult if you try to understand the code. So focus less on code in this video, focus more on what I'm trying to explain conceptually here. Okay, if you don't understand the coding part, it is totally fine, but just try to understand the visual part and the explanation, the logical explanation that I'm trying to do, because that is the base for the major algorithm that we'll be doing in future, that is binary search, binary tree, those kind of things which we'll be doing in future. So log n is a type of log n is basically used in binary search. So that is a part of our subject, but that comes somewhere around mid of the course. But I'm just trying to give you an overview of how log n looks like and how it is way more efficient than most of the algorithms. So let us start this particular video. Now let us say we have a simple task. Let's say we have a list of 8 elements. So let's say we have this list of 8 elements. Let me create this. Okay, so 1, 2, 3, 4, 5, 6, 7 and 8. So let us say this is the list that we are having. So far we have been doing a question where suppose you are given a target. Let's say you are given a target of 6. You have to search the target in this particular list and return its index. So how we have been doing so far, we have been using simple linear time complexity where we search one by one. For example, we come here, check if it is 6. If it is 6, then return the index. Otherwise, move forward, move forward, move forward, move forward, and so on till we find it here. So this is a simple linear time complexity because we are using entire list. We are searching everything one by one. Now imagine the number of data set size, let's say list size is 1 billion. Okay, and in 1 billion, your number of steps will become 1 billion. So linear search is good. I'm not saying it is not good, but when involving excessively high data, okay, this might not be the right solution. And there comes the concept of log n, and you can say binary search. So let's try to understand how binary search help me solve. So for example, in this particular scenario, 8 steps, this took me 8 steps. Ideally, I mean, it will take me 8 steps to find the right element, maximum inverse time complexity. But same thing, if I do using binary search, it will give me it. I'll be able to do in 3 steps. Okay, and similarly, 1 billion parameters. This particular linear time complexity will take 1 billion steps, 1 billion iterations or observation, but a log n time complexity will be able to do it in 31 steps. So I think you can see it is able to find an element in 1 billion data set in just 31 steps. And that is the magic of this particular algorithm which we are going to discuss. So right now we are just going to discuss the time complexity. Algorithm we'll be discussing once we started. So let's start breaking this thing once again. Let me create this whole list which is our target here. So let's say this is my list. Okay, so let's say this is 1. Again, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7 and 8. So let's say this is my list. Now what happens, what we do here, first of all, our first step is to split the whole list in two halves. So split in two halves. Okay, so let's say, so when you split it in two parts, so what you will be getting, you'll be splitting it from here, correct? So one list will be this, and so this will be list A and this will be list B once you split it. Okay, remember we are searching for 6. Now what you do, you ask yourself, so this is, or you can say left part, or and this is the right part of your split. Now you ask yourself one question, so whether your target lies in the left part or the right part. If it lies in the left part, you will drop the right part. If it lies in the right part, you will drop the left part. So what are we doing here? 6 is lying in the right part of our split, so we will drop the left part, okay, and keep right part. Okay, now once we keep right part, so what is my right part now like? So my right part will something look like this. It will be 5, 6, 7 and 8. Now I will repeat the step. Again, I will split it into two halves. Again, let's split in two halves. What will happen now? So it will become 5. So what is the split right now? This part is left, this part is right. Now ask yourself again this question. Where is 6 lying? Is it lying in the left part or it is lying in the right part? It is now lying in the left part. So I will drop this particular part. So fourth step will be drop right part. Now we are left with 5 and 6. So now again split the left part and see. So once you split this, what you will be getting? 5 and 6. You'll be getting two things. So this is the left part, this is the right part. And now ask yourself, where is this particular 6 lying? This is lying in the left or the right? This is lying in the right side. So you were able to locate this particular part. So now after splitting, you'll say drop left part, and this is your target. Now in how many steps were you able to do this? Your first step was to split in half and check. So this whole is one step technically, that you split in half and then you check where that element is lying. Is it lying in the left or the right? Wherever it is lying, you drop the remaining part. So this is the first step. The first part was to split from here. The second was to split here, and third was to split here. So in just 3 splits, you are able to get the target. Okay, you're able to get the target, and that will give you the location of your particular element. So I hope this particular visual explanation is clear to you. Let's try to understand it through another example. So let us say you have a list of 10 elements. Okay, now I will try to explain little fast here. So let us say you have 10 elements. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So what is our plan of action? First of all, we will split it into two parts. So the first split we will do here. Okay, so this is my left part, and let's say I'm searching for element number 4. Okay, and this is my left split, this is my right split. So this part will, because 4 is lying in the left part, so I will drop this. Now I'll be left with 1, 2, 3, 4, 5. Okay, so I'm left with 1, 2, 3, 4 and 5. Okay, now I will again do the splitting. Now the split can be either you can either do from here, you can either do from here. It's totally up to you. So for example, let us say I am doing from here. So what will I get? So I will be getting this part and this part. Now 4 is not lying in this, so I'm left with this particular part. Okay, so you are left with 3, 4 and 5. Three, 4 and 5. Correct. Now my target is to get 4. So now what will I have to do? I will have to further split it. So if you see that, so let's say I split it from here and this particular part. Now I know that it is present in 4, 5. So I will have 4, 5 here. Correct. And then I will split it again and I will get to see that 4, this is 4, this is 5 and 4 is lying on the left part. So technically what we are doing, we are splitting 1 split, 2 split, 3 split, 4 split. Okay, so this is what this is technically what the power of splitting, that the number of times we need to split our data, that particularly show us that these many steps are required, and effectively we will be able to answer our question in this particular approach. So just to keep a count of number of steps in this particular scenario, so one step was this, second step was this, third step was this, and fourth step was this. So total 4 steps were required for me to find an element in a list of size 10. Correct. Normally it would have taken me 10 steps if I used to do a linear search. So this is the power of log n time complexity. Now let us try to summarize this particular time complexity even more. So what do we see here is that now let's say we had a list of size 2. Okay, A, B. How many splits will you require to find the element A or B? You'll require 1 split. So when your data size, so let's talk about size of data set and steps required. When the data set size is 2, you require how many steps? You require 1 step. Okay, and when data set size is, for example, 3, so let's say this is A, this is B, and this is C. So how many splits will you require? First of all, you will need to split this A, and let's say this is BC. Okay, and then you will require 1 more split here. So it will be A, B, and C. Total 2 splits will be required. So in case of 3, 2 splits will be required. Similarly, in case of 4, you will require 2 splits. In case of 5, 6, 7, you will require 3 splits. And in case of 8, you will require again 3 splits. So if you notice the pattern, what is happening here, this is called, why this is called log n time complexity. Let me explain you. If you see this particular scenario, for 2, it is 1. For size of 4, it is 2. And for a size of 8, it is 3. Correct. So if you know the power of 2, how does it work? So the power of 2 works like this. 2 raised to the power n is equal to your data size. So this is how this algorithm works, is your data size. Okay. Now, so n is number of splits that is required. So if those who know how to convert this particular thing into log, so basically if you take log both sides, so how does it come out to be? Log of 2 data size is equal to n. This is the implementation of log. We don't need to go too much into maths. Just try to understand what this algorithm means. This algorithm means what power of 2 will be required to reach this particular data size. As simple as that. So for example, let us say you are given a data size of 16. the question will be that let's say you're given a list of size 16 and you have been asked to find an element inside it. So in log and time complexity, how to determine number of steps required, you will say what is the power of 2 required to be equal to 16, and that is 4. It means total 4 splits will be required to achieve this particular task. Correct? Now now let's try to understand the power of log and time complexity, which we were saying earlier. That, for example, let's say there is a list of now we know that 2 raised to the power 10 is equal to 1024. 2 raised to the power 30, so this is approximately equal to 10 cube. That is correct. Now if we see that 2 raised to the power 30 will be equal to approximately equal to 10 raised to the power 9, which is a billion, which is again we are saying a billion. Now if you see this, we require approximately, so let's say you're given a list of billion size, a list of which has billion inputs in it. Now to search an element inside a billion size of list, you only require how many steps? 30 steps. Okay, so this is the power of log n, that even it is very much efficient when you are searching for big data sets. It does not increase the number of observations or we can say number of iterations. So it is very efficient, again, as I mentioned. Now for example, even for 10 raised to the power, like you can keep on checking, right? If you do 10 raised to the power 18, we're doing a further square, so you only require 60 steps. In just 60 steps you can check billion, trillion, like those kind of numbers you can achieve. That is why log n is considered one of the most effective algorithms. So just let me give a summary once again. What is log n? So log n is simply 2 raised to the power n is equal to your data size. And how you visually imply that, how many steps, what is the power of 2 required to achieve the size of your given data? That is log and time complexity. Correct? So this is log 2 data is equal to n. This is the meaning of log. Now you can try to compare. For example, in the example of 10, when the size of your data is 10, so the power of 2 required is 2 raised to the power 3 is 8. So this is 8 is less than 10, so we will require 2 raised to the power 4. So which means we'll require 4 splits to achieve this particular task. I hope this explanation is clear to you guys. Now let's just move into a little bit summary. You don't need to focus much on code. I'm giving a code right now, but you don't need to focus on the coding part of it. Just try to understand this concept in mind. Okay, code we will be doing extensively once we start the binary search in detail. So we will now try to understand the concept of logarithmic time complexity or using binary search with a example here, and we'll do a parallel coding as well. Now beyond this point, if you don't understand things, it's totally fine, because things are going to be little advanced from here in this video. So if you don't understand, it's totally fine. I'm just trying to show you the implementation part, that how logarithmic time complexity is used in real world scenario. We'll be covering binary search, 2-pointer techniques in detail when we start the algorithms, so you don't need to worry about them. We'll have dedicated sessions for them. But right now, if you don't understand, don't panic about it. Okay, just be calm and try to understand what is going on, and it will help you. So now let's do one thing. Let's say we have this particular list. We have 10 elements inside it 3, 9 up to 33, and we have to find a target element 21. And if we find something, we have to return its index. So far we have been doing it through linear search. What happens is that you do one by one and you compare if it matches my target or not. But a linear search here will involve 10 steps. Now, can I do it in less than 10 steps? That is the question. And that is where binary search comes in. So let's start coding a little bit. So what we will do, we'll create a function def binary search. Okay. And this is your array and then this is your target which you are doing. Once you have done this, now let's see there comes now how does binary search work, that or you take the mid of you do splitting, right? So how do you do splitting? So for example, let's say I have this particular list present. So how do you do split? You define a left pointer, you define a right pointer, you take the center of these, you take the center midpoint of these two, and then you check whether your target element is lying in this or this. If your target element is lying here, you will drop this point. Okay, and if you again now this is your area of focus. Now in this again you will do a split and you will check whether it is lying to the left or to the right. So technically what we are doing, we are creating a left pointer here. So we'll create a left pointer. This pointer will be dynamic, it will move throughout the code, left and this is right. So let's say we have created 2 pointers here. Now let's write down them in code as well. So let's say this is left equal to 0 and right is equal to the right of the array. So how do we do it? We take length of array minus 1. This will give me the right pointer which is here. Now for every scenario of left and right, I need to create a midpoint. So how do we get that particular midpoint is that is interesting part. So for example, this is 0, this is 9 here. So I need center of this. So because this is the list of 10 elements, I will take 0 plus 9 by 2. Okay, this will give me 4.5. So 4.5 means I have to take the exponential part, the quotient part, so which is 4. So what is my index here? If you see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will be my midpoint here for this particular scenario, the index 4, which we just calculated here. Okay, so we'll write down this implementation in my code here. So in code, remember your left pointer always need to be to the left of right. This might sound very obvious because we'll be moving things here and there in the code. So your left pointer always need to be remain to the right of your right pointer. This is otherwise your right pointer will become your left pointer. Okay, so we'll be repeating things there. So while if you don't understand, that's totally fine. Again, I'm saying this left and right pointer, we will be covering them. So while left is less than equal to right, so what are we doing here? Now we have to create a midpoint. So how did we create midpoint? Mid is equal to left plus right minus left quotient 2. Okay, so this will give me the quotient part. Now I need to check whether so there can be 3 scenarios possible. If you remember, there will be 3 scenarios. Either your mid will, so let's say this is my target here, this is what I am looking for. Either your mid can, whatever midpoint you find, mid can be equal to target. This is what we want to achieve, correct? So or your mid will be to the left of your target, or your mid will be to the right of your target. So let me just clear this particular part so that you understand a little bit more. So what did I say? That whenever you create this midpoint, now there will be multiple scenarios. Let's say this is your target, which you need to find. Let's say this is your target. Now your midpoint can lie here, can lie here, can lie here. There will be 3 scenarios. If it is lying here, what you do, you take your left pointer and you move it to here. Okay, and the first thing, if your midpoint is equal to target, then your answer is done, right? So for example, the first condition that I'm going to write down is if your mid pointer is equal to the right pointer. So what we'll do, if array mid this is equal to target, then we are done, right? So what we need to do, just return your mid element, your mid index. That is fine. But so technically this is when midpoint equals when midpoint equals target, I'm sorry for this, equals target, and search is complete. Okay, so this is your ideal scenario, but what will be happening, it will not be that easy. LF, the second scenario will be that your midpoint can be to the left or can be to the right. So let's try to address when your midpoint is to the left of your target. So LF, array of mid, is to the left of target. So what is happening here? Now let's try to visualize in the code, in the diagram. Right now my midpoint is to the left point. So if you see, all the elements till midpoint are useless to me, because I know that my search element will not be lying in this particular part, correct? So I know that till midpoint this is of no use to me. So what I'm going to do, I'll be removing, not technically remove, I mean I'll shift my focus from these particular list. Okay, so these are not important to me right now. So technically what I'm doing, I'm going to move my left pointer to the right of mid pointer. So I'll move my left pointer here. So this will become my new left pointer. Okay, so this particular part is done. Whenever my mid element is to the left of my target, I will move my left pointer to the immediate right of the midpoint, because I am sure that I cannot find my target in this particular area. So this is my new search domain. Okay, and I will repeat the whole activity once again. So this is, for example, my new search domain: 21, 24, 27, 30 and 33. Correct? So this is my new left pointer and this is my right pointer. So let's, okay, so this was index 5, 6, 7, 8, 9. So let's do one thing. Let's try to redraw it in the new screen. So this is my new screen. Now this is my new left pointer. Okay, and this is my new right pointer. Now what will I do? I'll create another mid pointer. Now what will the midpoint of this particular element? It will be this. So this is my mid, and remember this is my target still remains 21. So how do, now my midpoint is lying to my right of my target. So whenever such scenario happens, I have to move my right pointer to the immediate left of mid pointer. So I will move it from here to, this will become my new right pointer. Okay, and this will come down to 21 and 24. 21 and 24. Okay, and what will happen? This is my new left pointer and this is my new right pointer. Now I will again find the midpoint. What is the midpoint? It will be this. Okay, so now when I search this, when I created another split, so this is my new midpoint. Now my midpoint is equal to my target element. Correct? So here my midpoint became equal to my target element and my search is completed. Okay, so this was the scenario. So how many splits we required? Approximately 3 to 4 splits. So this was the scenario. Now let me complete this particular code. If this is to the left of target, what I need to do, I will move my left pointer equal to immediate right of mid. So mid plus 1. So here what is happening, that my target, okay, is greater. My target is greater. So ignore the left part of search, or you can say list. Okay, left part of search or list. The third scenario, what is going to happen is, else if my array mid is greater than target, okay, then what I'll do, I'll shift my right pointer equal to mid minus 1, and this will do, these three loop things are enough to complete the code, and eventually if I don't find anything, return me -1. So this will be the implementation. Now let's try to search is using binary underscore search. Let's pass this array and target. So it should give me result. I have got 5. What is 5? It is this particular element. So 0, 1, 2, 3, 4, 5. So this is how binary search is implemented using various splits in the code. We'll be covering this type of algorithm. There are like lot of questions which are based on binary search, but this is the, I will say, concept building part of it, and this is called log n time complexity, because how many times we are actually so what is to the power of 2 required to reach the particular data size, and that is called log time complexity. Now let's try to plot the complexities that we have seen so far, so that you guys can, I can show you where does log n lie with respect to others and why it is one of the best time complexities. So far we have seen that, so let's say this is my graph, this is my data size, okay, and this is my operations. So what happens, we knew that the constant time was this is O1, okay, this is ON. There you will find polynomial, for example ON square and cube, whatever things. This is the exponential time complexity. So this is 2 raised to the power n or 3 raised to the power n. The best thing about, so you see that this is the best time complexity. As we move here to here, things improve. Now what did we see? That log n was better than linear search, because a linear search for 1,000 element will take 1,000 steps, whereas a log n will only take 10 steps. So that is the thing. Log n technically lies somewhere around here. This is O log n, O of log n, and that's why this is considered one of the best algorithms to find elements or iterate over things, like whatever you see. So this is the implementation of O log n. This is n. You see that it is not as good as like constant time complexity, which is very obvious because we have to search an element dynamically, right? But it is still way better than a lot of algorithms. So these are the major algorithms that we will be using extensively in our course. That is constant time complexity, linear, polynomial, sometimes exponential. There is another time complexity which is called as n log n, which is a merge sort, which is technically used in merge sort algorithms. It lies somewhere here, okay? So I'll be covering that in next video as well, but don't worry about that. Just try to focus. Our 80 to 90% of the questions will lie in ON, log n, and ON square. So major questions will lie in this particular scenario. So just focus on this part, and it will be good for you. So let me know if you understood this particular. I know this was little advanced, log n, little bit advanced than our linear time complexities that we have been doing, but I tried my best to explain it. Still, if you guys don't understand, please comment below, and we can discuss it in the live session as well, or like through any other method. So thanks for watching this video. Please stay tuned to our channel and this course. We have a lot of exciting things coming up. In the next series of videos, I'll be talking about, first of all, n log n time complexity. Then I'll be talking about when you have in a single code multiple time complexities. So how to determine the most effective time complexity, or how to compare codes, because that is very important part in the syllabus. So we'll cover that in the videos that are coming to be on Thursday. Right, so that's it from me today. Have a good day, and keep learning, and I'll see you in the next video.